consider the eigenvalue problem. Let's say consider eigenvalues and eigenvectors. All right? Let's just do it like this. Q psi is equal to lambda psi. Okay. So first of all, because of the second condition, this implies that lambda is real. I think this is not necessary in here, but there are some other implications of that thing in here. So because of this first condition, we can have this. So if you look at Q squared psi, you can easily see that this is lambda squared psi. Okay. And since if this is equal to the same thing as Q times psi, which is basically lambda psi, right? Q and Q squared, they are equal to each other. This would then imply that lambda squared is equal to lambda. Well, basically lambda minus 1 is equal to 0, which means that the eigenvalues are either 0 or 1. So let's say it like this. All eigenvalues of Q are 0 or 1. Okay. So in any case, so because of this fact, I actually don't need this property in here. So that's obvious. But there's another thing in here that basically this is a property of the Hermitian operators. So the eigenvectors corresponding to different eigenvalues are orthogonal to each other. So let's then do it like this. So the second property therefore implies that, right? Let's say it like this, right? Let's say let psi 0 be a 0 eigenvector corresponding to 0 eigenvalue, and psi 1 be a eigenvector. I don't think that this is the correct notation. So because of the Hermitianness, these two eigenvectors should be orthogonal to each other. So their inner product is equal to 0. So the Hermitianness somehow enters into this. Okay. So what you do is this. So define eigensubspace corresponding to let's say eigenvalue lambda equals 1, right? I'm just going to call this as, I think I'm going to use curly W for that. So these are all vectors of the form where Q applied on psi is equal to psi, right? I mean, all of the eigenvectors with corresponding to eigenvalue 1. This is called an eigensubspace, right? So this might be one-dimensional, but usually there is a degeneracy. So as a result, this doesn't need to be one-dimensional. So it just depends on the situation. Okay. So as a result, you can see that W perp is basically the orthogonal complement of W. Because of this property in here, all of these vectors in the orthogonal complement should be eigenvectors with eigenvalue 0. So therefore, this is the eigensubspace, let's say, corresponding to lambda equals 0. I mean, all of these 0 eigenvectors should be in the orthogonal complement, and you can also show that this is vice versa. So as a result, I'm just skipping some of the details in here. So if you want to write this thing down in terms of this set constructor notation, these are formed from all vectors where Q applied on a vector gives you 0 eigenvector, right? Let's define it like this. So this is a cartoon picture. So assuming that the whole space is 3-dimensional, it might appear that W is 2-dimensional like that, in which case W perp would be this 1-dimensional space. So that subspace is perpendicular to that one. Okay. So next thing is that we can express, this is a property of the all Hermitian operators. So somehow the eigenvectors of the operator form a complete set. So you can actually form a basis out of it, but I don't want to go into that kind of a detail. So we can express any vector, right? Let's say it like this. So we have some kind of a vector in here. I'm going to call it as alpha. I'm using the cat notation for vectors, but it's just alpha in here. I can write any vector alpha as a sum of a vector in W and a vector in W perp. So I'm just going to call this like alpha parallel. I don't know. I should call this a, yeah, let's say alpha parallel in here. So I'm basically going to repeat what I have said earlier. So in any case, I'm just going to write therefore that it's the same picture again. Alpha is a sum of a vector in the subspace plus another vector in the orthogonal complement. In this case, you can see that Q applied on alpha gives you, let me write this thing down correctly first. All right, this is a zero eigenvector, so therefore it's, this is going to give you zero. So this is basically one eigenvector, so therefore this is going to give you alpha parallel. All right, so therefore this Q basically applied on alpha gives you the component of, I mean, it basically gives you the this vector within the subspace W, right? So this is the, so therefore Q is the projection operator onto subspace W. So you can then check the other properties, but I don't want to go into these. How did the orthogonality enter into the picture? Because we said that this W perp and W are perpendicular, sorry. How did the orthogonality enter into the picture? Because of this property. I said that zero eigenvectors and one eigenvectors, these are orthogonal to each other because the operator is Hermitian. Eigenvectors of Hermitian operators are perpendicular to each other, orthogonal to each other, if the corresponding eigenvalues are different. I'm using this fact, then I'm using this fact to say that this subspace is a subspace for zero eigenvalue. And somehow, therefore, when I apply Q to any vector on that subspace, especially this vector in here, it gives you zero. So whatever, at the end, we get an orthogonal projection. So the fact that the projection is orthogonal is related with the fact that Q is Hermitian, all right? So that's the one that I need to stress on this. Okay. So if it's a, therefore Q is an orthogonal projection operator, so therefore it's a geometric projection, and there's this vice versa thing in here. So if you just think about I mean, if you define the operator as a geometric projection thing, then you can actually show this other two properties, that Q has to be Hermitian and idempotent. Okay, so because of this reason, we say that, right? Let's say there is a one-to-one correspondence between subspaces W and their corresponding projection operators. Q, right? There's some kind of a correspondence in here. I'm just going to write down some correspondences in here. So there's a subspace in here. If the subspace is W, we said that the operator is Q, right? It's the projection operator. All right, when I say projection, it's always orthogonal projection, right? I never talk about non-orthogonal projections. So this subspace corresponds to that operator. It turns out that the orthogonal complement corresponds to 1 minus Q. Identity minus Q, right? I'm just going to write it down like that, okay? Identity is just an operator. So it turns out that if Q is a projection operator, then 1 minus Q is also a projection, okay? If the subspace is the 0 subspace, this is a trivial subspace. In that case, the corresponding projection operator is the 0 operator. If again, this is trivial subspace. If the space is the full space, I didn't give a name to this. Did I give a name to this? I think I called it as V or something like that, right? I think on Monday I did this, but in any case, I might have forgotten. So the identity operator, let me put hats in here so that, I mean, this is not really one, it's the identity. I think I should write I in here instead of one, so that's kind of better. Right, you can check that these are basically projection operators, right? They satisfy all of these two essential properties, okay? What is interesting in here is that if, let's say W corresponds to Q, and another subspace W prime, for example, corresponds to Q perp. So sorry, Q prime. Sorry about that. Different subspaces correspond to different operators. Let's say and, right? If then this is something that we can say. These two subspaces are perpendicular to each other if and only if the product of these two operators is equal to 0. So I can actually understand the orthogonality of two subspaces by just doing some kind of an operator calculation. So if the product of these two operators is equal to 0, then the result is true. The order is unimportant, so let me just add this. Because if you take the Hermitian conjugate of that equation, you get Q prime Q is equal to 0 as well. So you need to check only one of them. So the other one automatically follows. And then based on this, you can basically say that the subspaces are perpendicular to each other. So here, for example, you can easily check that Q and identity minus Q is equal to 0. This is the idempotent property. Therefore, these two subspaces are orthogonal to each other, all right? So in any case, mathematically, the point is this. There's this geometry of the subspaces and the angle between subspaces and things like that. And then there's this operator algebra. We make some kind of a connection between these two different mathematical things, right? That's essentially what it is. Okay. So having said that, let's just forget about everything about this and then come back to the thing that I have started on Monday. Basically, let's just start this, right? I'm going to do it like that. So I have, let's remember this. So G is a finite group, right? G is a finite group. U, mu are the corresponding irreducible representations, all right? But we have this usual notation again. So A is a representation, any representation, all right? So this is a representation that we obtain at the beginning when we start solving a problem. So as a result, it doesn't have to be irreducible. Um, it's a representation of G on vector space V. Okay, so there's also a decomposition of this thing in terms of the U mu. All right, so we define these operators. So the first one is this. It's the P mu ij. This is defined like that. It's the dimension of the mute representation divided by the order of the group and sum of this. But we just write down the matrix elements in here, and then we basically write down the complex conjugate. But we take the linear combinations of these things in here. Okay, so first, the second one is this. This is P mu. It's just sum over I of P mu II. And then I said that this is equal to d mu divided by the order of the group, sum over the group elements, and then we have the characters in here for the irreducible representations. Okay. And then I have shown this, that P mu is Hermitian, and P nu product is equal to delta mu nu P nu. Okay. So we then deduce these two properties, but concentrating on this. All right. So let's then talk about this. So especially if I take mu equals nu in this equation, this is basically an idempotent relationship. So this implies that for each irreducible representation mu, this operator that I have defined is an orthogonal projection operator. Okay. So this is an orthogonal projection because they satisfy those two properties. So therefore, so as a result, P mu is projecting to a subspace. Let's call this as W mu, all right? To some kind of a subspace. So this is the first property. The second property is that because of the fact that, so let's say, since when mu is different than nu, this equation basically tells me that the product of these two projections is equal to 0, which means the same thing as saying that, which means basically if mu is different than nu, then these subspaces are orthogonal to each other. Okay. So as a result, I have some projection operators to orthogonal subspaces. All right. What else? So another thing in here, right? For each mu, W mu is an invariant subspace. Okay, but I'm just going to say this. I discussed this on Monday, but I'm not going to repeat this thing in here. So let me say it like this. So W mu can be considered as a direct sum of many subspaces such that A behaves like U mu on these subspaces. I think this is actually kind of complicated to express, but in any case, here I'm just identifying the subspaces, the invariant subspaces, consisting of vectors which transform like the muth irreducible representation. This is the procedure that I would like to follow. So use these projection operators to identify these subspaces. How can I find the subspaces? Just take any vector alpha, apply p mu to alpha, and the resulting vector is, if it is non-zero, is just an element of that subspace. All right? That's the thing that I'm going to do. Okay, so here, I don't want to go further, but you can go further actually. You can talk about like these irreducible sets and things like that. Instead of using these projection operators, you can use these ones. These are also projection operators. They are Hermitian and they satisfy the idempotent property. You can also use them too. I don't want to do that, right? So what I want to do is basically this. These are examples, just simple examples. Okay, so the first example is from this problem. I actually ask you to remember what the problem is. I'm not going to go over what the problem is, right? If you remember, we have solved this problem by using group theory. This was a very simple problem, but so, I mean, we didn't need the group theory to actually solve this problem, but in any case, here the representation, the group was this, right? Group was equal to C2. There's a special name for that group, but in any case, it contained this identity and this reflection, if you remember. The representation was A. So A was just actually a 2 by 2 matrix. So A of identity was identity. And A of sigma was this thing, right? It is 0, -1, -1, 0. If you remember this, this thing in here, if you remember this representation. So in any case, from here, we said that this group C2 has this character table. This is identity element and sigma. This is U1, U2. The character table was this. And since the character of A was like 2 for identity and 0 for this one, and then from here we then deduce that A is just the direct sum of these two representations. Okay, and the question is, which subspace? This basically tells us that there's a one-dimensional subspace of vectors which transform like U1. There's a subspace of vectors which transform like U2, right? So let's just call this. So W1 is, I'm going to use the curly symbol in here. So this is a subspace of vectors in the vector space V, whatever, that transform like the U1 representation. And there's a second subspace. We have already found this, but this time I'm going to find them systematically. How? Well, by computing the projection operators. So I know what the formula is. So I know these matrices, right? I just need to take their linear combinations. Okay. How do I do this? All right, let me do it like this. All right, so P1, I'll start with P1. So let's remember that this is D1 divided by the order of the group and the sum of the group elements of, and then the characters of G complex conjugate and A of G. Okay. The dimension of the representation is 1. Order of the group is 2. I'm just going to start with the, yeah, I already started with the trivial representation. So this is, these are my characters. So this is 1 times A of identity, and then 1 times A of sigma. Okay, I already have the matrices, so therefore this is 1/2 of 1 minus 1 minus 1, 1. This is a projection operator. You can check that easily, and I don't want to do this, right? So let's then compute P2. Yeah, I'm just going to do this from memory, right? So therefore, this is 1/2 again. The characters are 1 and minus 1. And, well, I just need to use these two. So in that case, you can see that the projection operator is really these. So check that, for example, P1 squared is equal to P1. And P2 squared is equal to P2. These are really, the idempotent relationships. It's easy to see that they are Hermitian. So as a result, no need to check this. But you may want to check that they are perpendicular and their product is equal to 0, right? Just check that this product gives us a 0 matrix, or we can check it in the opposite order. All right. So, but still, these are operators. I don't have the subspaces. So as a result, what I do is like take an arbitrary vector alpha. I don't know. Let's say that this is 2, 3, right? Or 2 minus 3, or I don't know. Even this is usually people just choose a simple one, right? Like this first basis vector. Yeah? So what we do is this is the space. This is the subspace. You can think of it like that. All of these alphas and things like that, these are actually vectors in here. So probably this alpha corresponds to this vector in here, that point in here, whatever. So we first compute P1 applied on alpha. What is P1? It is this thing in here. You can easily compute the expression. So you basically get this vector in here. It's just arbitrary, but it's a vector in the subspace that we are considering. So that's the U1's, this is the W1 subspace. Once you find a vector in that subspace, a single non-zero vector, you have essentially identified this one-dimensional subspace, right? So what we are doing is basically taking this projection in here. So this is basically P1 alpha in here. Okay. Second, let's compute P2 applied on alpha. That's also very simple. So we get 1/2 of 1, 1. So I suggest that you actually try different alpha vectors in here. You're going to get different vectors, but eventually you're going to see that you always get the same subspace. Okay? So in that case, this is the projection, and this is the second subspace, and this is basically this vector in here is P2 applied on alpha. Okay. But if you remember, when I solved this problem formally, I have identified these two subspaces by inspection because it's quite easy to see. But if you want to do it formally, you can do it like that. Okay. So for low dimensional vector spaces, probably you can use your intuition. You don't have to use these projection operators and things like that. But in higher dimensional vector spaces, like, I don't know, in let's say 9-dimensional vector space, it's actually quite hard to visualize things in there. So as a result, these kind of projection operators might be very useful, right? That's why I'm describing these. So these projection operators are essentially used for finding the invariant subspaces of the representations. All right. So that's the end of that example. Let's just look at this another example. I also talked about this representation. So let's say another example in here. All right. in that case, the group is S3. If you remember. So these are the permutations of three elements. Sorry about that. We know this group quite well. We talked about this representation. Let's say it like this. A is, let's say A of G is the matrix permutation. Matrix permutation of G. Basically, I can think of A of G as the permutation of the three standard basis vectors. If you remember, we had these, like, for example, A of, let's say, 1, 2, 3 is this matrix, if you remember. So the first column gives us the second standard basis vector. Second column gives us the third, and the third gives us the first standard basis vector. Let's say, etc. Okay. This is the representation. Okay. So let's then write down the character table. Sorry. So that's the character table of the group S3. So we have identity. I'm writing the classes in here. These are the conjugacy classes. So these are the transpositions, and we have the three cycles in here. So there are one element in here, three elements in here, and two elements in here. And I have also called the representations as U1, U2, and U3. I didn't give any special names to these. U1 is the trivial one, U2 is the signature, and U3 is the two-dimensional representation. And I think I got 0 in here and -1 in here, right? These are the representations. Okay. What are the characters of A? Well, the character of identity is equal to 3. For the two cycles, the character is equal to 1. And for 3 cycles, the character is equal to 0. Okay. In that case, therefore, for this case, we find A to be equal to is a direct sum of U1 and U3. Right? U2 doesn't appear in here. And so we have U1 and U3 in here. So how do we compute? So therefore, I mean, let's just compute the projection operator for the trivial representation. So the dimension is, right, let's just write down the formula again. All right, this is that sum. All of the characters are equal to 1. So therefore, I need to add up all of these representation matrices, all of these matrices of that form. Right? There are 6 such matrices. So as a result, this might appear like a complicated summation procedure. But we can do it, actually. I don't want to do it explicitly because I know what the result is. I know that for each entry, of course, there are actually 2 permutations there. This entry is equal to 1. So therefore, we get, like, I mean, each of the entries would be equal to 2 in here. So as a result, the final result is this. This is the projection operator. Check that this is the case. I mean, just convince yourself that the first projection operator is this. This is also a one-dimensional projection, so you can actually look at the projection dimension from here. So you just need to look at the trace. If the trace is equal to 1, then it's a projection to a one-dimensional subspace. But you can easily see that this projects to space, to the space. Spanned by 1, 1, 1. Right. We already knew this, of course. We have talked about this thing before. So we said that this vector is left invariant by all the permutations. So therefore, the trivial representation has this invariant subspace. So I can then identify the invariant subspace corresponding to the U1 representation. Now let's go to U3. So the nice thing in here is that we have identity, and these two things have non-zero characters. So as a result, there are only three terms. So I'm going to write P3 in here. Okay. The dimension of the representation is 2. Order of the group is 6. Character of identity is equal to 2. That's the representation matrix for identity. Character of the 3 cycles is equal to -1. So let me write it down like that, okay? So the first one is 0, 1, 0, 0, 0, 1, 1, 0, 0. And the next element is this -1 times 0, 0, 1, 1, 0, 0. Let me first write and then discuss later, right? So this converts 1 into 3, 3 into 2, and 2 into 1. Yes, that's 1, 3, 2. Okay, so that's the matrix in here. So you can see that all off-diagonal entry is equal to -1, and diagonal entry is equal to 1. Is equal to 2, sorry. So that's the 2, -1, -1, -1, 2, -1, and -1, -1, 2. This is P3. Okay. So there's one other thing. So I'm going to also claim that P2 is equal to 0, because the second, we don't have U2 appearing in this here, but let me just forget this for a moment, right? So what I do is this, so just take an arbitrary alpha. Okay. Apply P3 to alpha. So let's say, I don't know, alpha is equal to 1, 0, 0. I mean, it can be anything, 1, 2, 3, 1, 2, 5, or something like that. So that's also a possible thing, right? It doesn't matter what it is. Again, in some cases, of course, you choose it in the wrong way so that the projected vector becomes 0. So in that case, yes, it matters, but you just try many things, right? That happens. Okay, I mean, let's just choose it like that. So that's arbitrary. In any case, so P3 applied on alpha, then that's going to be what? Yeah, let's just write down all the matrices in here, sorry. All right, so that's 1, 2, 5. This is, all right, so 2 times this, 2, -2, -5. So the first entry is -5. And for the second entry, I have 4, -6, so that's -2. And the last entry, this is 10 -3, so that's 7. Okay, so that's one of the vectors. Okay, but this was a 2-dimensional subspace, so as a result, there's another vector in that subspace. In that case, just choose another alpha, for example. That's a possibility. Or what you can do is, I mean, you know that this is, let me call this as alpha 1, for example. You can apply any of these, I don't know, permutation operators, any of these A of G, on alpha 1, in that case, you are going to get another vector in the same irreducible subspace, right? So let's say it like this. This is another vector in the same irreducible invariant subspace. Yeah, okay, whatever. So that's basically what you need to do in here. But if you actually used 1, 0, 0 in here, you would have a very nice value. But in any case, the essential point in here is that in all of these cases, you will get a vector where the sum of the entries is equal to 0. If you remember, this was the description that we have used for this invariant subspace. So finally, let's talk about this P2. So that's D2 divided by the whatever. So that's chi2 star G. Just check this, right? Check that this indeed gives you 0. Okay, so in that case, there is still a projection operator in here. 0 is a projection operator, but it basically projects to this trivial subspace. This essentially implies that basically this representation A doesn't contain any subspace, does not have any invariant subspace that transforms like U2. Let me write it down like that. Okay, so that therefore means that it's not A2. A does not have an invariant subspace such that A behaves like U2 on that subspace. There is no such subspace. Okay? But, I mean, usually you don't need to do this calculation because before everything, you should have actually obtained this, you should have obtained this decomposition. So as a result, if it happens that one irreducible representation doesn't appear in there, then you don't start with this. Okay, so that's the last time that I'm going to talk about projection operators. Since I'm not going to solve problems too complicated, so I don't need to use these kind of things. But in some certain applications, it might be necessary to use these operators. Okay. So I think I'm going to finish it in here. All right. So next week I'm going to start with this, with the quantum mechanical problems. I'm not going to spend too much time on that one either. So I'll be solving some simple problems actually, with mostly the s orbitals. Then if I have time, I will also talk about these, I don't know, the tensors in some crystals with some certain symmetries. Some certain tensors like the conductivity tensor and things like that. Because of the symmetry, they also have some special structure. We will talk about that, and then well, I think with this we will finish the whole semester. All right, let me stop here.